Hello and welcome to another video for Maths High Level. I'm going to talk about truncated MacLaurin series. Now it sounds horrible, right? Because already MacLaurin series were confusing, and now we're going to truncate them, and that might even be a word not really sure what it means. Now all it's going to be is that I'm going to approximate values. Now think about it. We said that e to the power of x was this long big thing here. Well, I can approximate that e to the power of 2 just by taking this. And I know that this thing is going to converge. You can check that using the ratio test. And if I add all of these things here, and if I find out what it converges to, and I keep adding them, I keep getting closer to this value here. And that's how it works. And that's kind of neat. So if I want to calculate this thing, I can actually say, okay, let's find out how well it works. Now, think about it. I can actually just calculate e to the power of 2. I can type it into my calculator and figure it out. Let's see how good this approximation is if I truncate this series, if I stop putting more and more terms at the 6th term, for example. Let's stop when k equals 6. So it's actually the 7th term, excuse me. So if we do that, if we say, okay, e to the power of 2, that's going to be more or less, because, like there are other terms afterwards, but I'm just going to ignore them. I'm just going to say, well, who cares? I mean, they're probably going to be quite small anyway. So let me just figure this one out then, right? Let me just stop at k equals 6, at the 7th term. And I can calculate these and just add them. And, they're just fractions. So, I mean, I can even do it without a calculator. And this is what I'm going to get. And if I make this division now using a calculator, this is the decimal I get, 7.356. Now, if you actually calculate e to the power of 2, this is the actual value, right? Okay. Well, I mean, how far is it? It's not that far. I mean, it's kind of close, but it's not that close either. It depends how good the approximation is. And that's going to depend on when you stop. Does it depend on other things? It kind of does depend on other things, but mainly like when you stop. I mean, if you stop at the 7th at k equals 7, it's going to be a worse approximation than if you had stopped at k equals 15. You keep getting closer and closer as you add terms. So we're gonna show you a tool that helps us figure out how close are we to the actual value. It's not going to be that easy most of the time. We can't just say, well, e to the power of 2, it's as simple as that. It's going to be this thing here. No, it's not going to be always that simple. Most of the time, we're not going to know what the actual value is. And we're going to only have this to determine what the actual value is. So it's not going to be as easy as just subtract and figure out how far we are. But we're going to have a tool to figure out how big this error at truncating at a given value is going to be. It's called the Lagrange remainder, and it's really not very complicated. And of course, you have it in your formula booklet, so no hard memory involved here. So if you have a MacLaurin series, and here remember this is the formula for MacLaurin series. If you have a MacLaurin series, then I mean all you have to do if you want to calculate the remainder. And think for a second here that this is a truncated at n MacLaurin series. It's truncated at n. See, I stop at a given value n. Then the remainder is going to be given by the next value. Simple as that. Just do the next value, and that's the remainder. Now, this sounds like something is wrong here. And what's wrong here is the c here. And hold on a second. What is the c here? Well, that c is going to be a value between 0 and x. We don't know which one. We don't know which one. But we don't need to know which one. So this is really the formula of the remainder. The important thing to remember is that c is a value between 0 and x. In a MacLaurin series, you will see that this changes when we talk about Taylor series. But c is a value between 0 and x. So how do we use this thing here? So it's the next term with a value between 0 and x substituting. Okay, it's a bit confusing. So how do we use it? Well, suppose that we stop at n equals 0. Now, sorry for a second. I'm not actually going to use it. I'm going to explain to you why. And I can't really give you a very rigorous proof of why, but I'm going to give you a hint of why this is the remainder, okay? With this crazy idea of a z between 0 and x. Where does this come from? Give me some narrative here, please. So suppose that would stop at n equals 0. Suppose that we say, okay, I'm going to truncate my series here. Well, that's not very good, is it? I mean, they have a lot of stuff left behind. Fair enough. But let's calculate this remainder thing in that case. Well, you know, in that case, it would be that f of x would be equal to f of 0, right? Plus the remainder at 1, right? Or r1. So that would be this thing here, right? The derivative, and we can substituting with c divided by 1 factorial times x, knowing that c is a value between 0 and x, right? Just use this thing here. And if I move this around, if I take this thing here subtracting, and then I take this x dividing, I'm going to end up with this thing here. And you have seen this thing here before. This is the mean value theorem. And it works for a value of c between 0 and x. So that's kind of why this thing works and why we have this idea of a c being between 0 and x. It's just something related with the mean value theorem. Now, you don't really need to know this. You don't really need to know this. To be honest with you, this is just an opportunity for me to remind you about the mean value theorem, the kind of stuff you keep forgetting because you keep worrying so much about improper integrals and all these series and the MacLaurin, Taylor, etc. Oh my God, and they forget about this mean value theorem, which is very important. And you know, those exercises of mean value theorem, they never look like they're exercises of the mean value theorem, which is why I worry about them. But anyway, back to MacLaurin series, truncated MacLaurin series, and the remainders. So let's use an example. So they asked me to find the first three terms of the MacLaurin series approximation of sine of x, and to use the Lagrange remainder to evaluate how big the error is if we use it for x equals pi thirds. Now I'm going to take from our formula booklet. Here is what it says about sine of x, and if I use the first three terms, right? This is the approximation. This is the truncated series for the first three terms. There you go. Did it. Some points here. I'm sure you know that the exam won't be that easy. So what is the Lagrange remainder? Now this is when it gets tricky, because you see here you have x to the power of 5. And people are tempted to say, well, you know, 1, 2, 3, I have to take the fourth derivative. No. This is x to the power of 5, so what's happened here, that you can't see it anymore, is a fifth derivative. So in your remainder, you need to take the sixth derivative. And just plug it in and calculate the sixth derivative of f of x. First one is cosine of x, second one is minus sine of x, third one is minus cosine of x, fourth one is sine of x, fifth one is cosine of x, sixth one is minus sine of x. And yes, these derivatives, the roots of trigonometric functions, form loops. They keep coming back to the same original value. They're cyclical. If you know the cycle, that's wonderful. But if not, just calculate it like I just did. So this is the one we're going to need. Minus sine of x. Wonderful. So there's substitute. That's simple, right? And I know that if x is equal to pi thirds, then this is what this is going to look like. Yeah, just substitute with the x. Now the c, we still don't know what the c is. We know it's between 0 and pi thirds. That's what we know. So this is the error term. This is an important thing to understand. This is the error term. So let's make it as big as possible, and then we won't be wrong. When is this thing going to be bigger? When is this expression going to be bigger? Let's take that value of c. In this case, it's going to be when c is equal to pi thirds. That's when this is going to be bigger value, and it's in the numerator, hence that's when it's going to be the biggest error. This is going to tell me the biggest possible remainder. I calculate it and I get the remainder. Now in this case here, it's negative. Now all it means is that this is how close we are. I could take the absolute value of this thing and say like, well, this is like how far we may be. I'm just going to leave it like that anyway. 0.00159, and that is how big the error can be. Might be smaller, but that's how big it can be. So when can I use this MacLaurin series stuff? Because remember, we supposed that we can write the function as a series. we can use them for any values of x such that the remainder is equal to 0. That's when we can use them. And if the remainder keeps getting to 0 as n goes to infinity, it means that we're getting closer and closer and closer and closer and closer and closer to something, not further away. That's going to be when we can use Maclaurin series approximation. That's our sign. And if you think about it, let's use this for an example. Let's use this idea. Can I use the series approximation of e to the power of x for any value of x? Can I? Let's find out. Now, I know that the nth derivative is always going to be e to the power of x, so the remainder, if I have to do, you see, the infinite derivative, right? The n plus 1 as n goes to infinity derivative of the function, it's just going to be e to the power of c, all right? And I'm going to get this expression here. And this is a constant, so I can take it out of the limit. And I end up with this thing here. And this thing here is something that's always going to happen when you're trying to use this thing. When you're trying to use the remainder idea and calculate the limit of the remainder as it goes to infinity, you're often going to be finding this limit. And this limit it doesn't have an easy proof that it goes to 0, but it does. And I'm going to explain, I'm going to give you proof after this slide. But most of the time, you're actually going to be given some clue. You have to prove it. And you can just go ahead and say it goes to 0. I think that should be fine. I should check with some of the mark schemes, see if at any point you have actually asked for you to prove that this goes to 0. I doubt they would. But to give you an idea, if you don't want to watch the next slide, because this is already 11 minutes and 40 seconds, to give you an idea, think of that, if you have an x, that's doesn't matter what the size of x is, right? We say like x is 2. Think about how many numbers bigger than 2 I'm going to have here, right? So of course it's going to go to 0. It's not a very rigorous proof, but that's roughly the idea. And if this goes to 0, then this thing goes to 0, right? So whatever value of x has, doesn't matter. It's going to go to 0. And that's the whole idea. So let me go through that limit quickly. You will often end up with this, and I'm going to give you a way to solve the limit. But most of the time, there's probably going to be something in the exercise that you should use to prove the limit, because there are multiple ways of proving this one. I'm going to go ahead and use the explanation that I found more understandable. So let's assume for a second I'm going to build a completely different series that afterwards is going to show up on my proof. If we have a big N that's bigger than x, then I'm going to end up, and have this limit. I know this converges, right? Because it's smaller than 1. So the limit is going to go to 0, right? This must be equal to 0 because I know the geometric series converges. So the limit must go to 0. Remember the divergence theorem. So at some point, on its way to infinity, n is going to be bigger than this bigger n, right? So this is what's going to happen. This thing here, stay the same in the numerator, and the n factorial, well, it's going to be n times n minus 1 times a lot of stuff in the middle. Forgot to put a lot of stuff in the middle. I think it's disappeared for some reason. But a lot of stuff in the middle, and then n plus 1 times n minus 1 times a lot of stuff in the middle, and then all the way to 0. Now, this part here is n factorial. And this part here is n to the power of how much? Well, how many n's do we have in total minus how many n's do we have in total? Like this thing here, sorry, it's not equal to that. This thing here is bigger than this thing here, right? Because this is just like n, right? N plus 1 is bigger than n, so n times n times n. This stuff here is bigger than that. So actually, because this thing is bigger than this thing is bigger, right? I just made this denominator smaller. Think about this one. It's not very easy to see. Apologies. I just made the denominator smaller. Hence, this thing here is bigger. Now, let me just rewrite, right? I have minus big N here, so I can put that in the numerator. And this is just a constant, so I can take it out of my limit. There's no small n here. And this is what I earlier on proved that it went to 0. So this limit, hence, right, is smaller than the limit that it goes to 0. And bigger than the limit You want to find that it goes to 0, so the limit itself goes to 0 by the squeeze theorem. Just a proof of this complicated limit that often appears when you're trying to show that a Maclaurin series converges for given values of x. Now, most likely they will ask you to go ahead and prove it and give you some clues on how to do it. But here's the solution itself. Excuse me, because I did forget to mention that there are a lot of other values in between here and here, and a lot of other values in between here and here. Thank you very much for watching. Goodbye.